Hello everybody, welcome to the EEL 3004 final exam review session. So today is going to be a little different. It's, for those that come to my sessions regularly, it's going to be like a little less hands-on because I have to sort of present up here. But still going to ask questions, still want you guys to answer questions if you guys feel comfortable with it. The agenda for today is we're going to go over the practice final that Chan provided you guys. We're going to go backwards because the final exam is more on the stuff he's gone over recently rather than the past stuff. So hopefully we'll be able to get to the past stuff. I feel like we'll go through it pretty quickly. So if we get done with it too fast, I still have older stuff we can go over from my past reviews if we want to do that, stuff like that. Okay, so let's get started here. I'm going to be juggling things a lot, so hopefully I don't drop things. Okay, so we're going to start with number 8 on the final exam review. And I know a lot of you have probably already done this since it's the day before the final, but these problems, you can do so many different ways. I probably did it differently than you guys. So you'll still get something out of it. Okay, so we have 4 parts to this problem. Part A is the load impedance, Z low. We know that Vs is equal to 100 angle 0 degrees, and that's volts, and it's also root mean square value. So we have to, part A, determine the load impedance, Z low. So the load in this problem is really just all the elements that are absorbing power. So we're just going to find the Z equivalent, basically, as seen from the source's perspective. So I'll do part A under this. Z low. So I'm not going to redraw it with the circuit removed. If you just imagine this, or sorry, the source removed. If you just imagine the source is gone, we're trying to find Z equivalent from that perspective. So we'll just go ahead and do that. Z equivalent is equal to 10 minus J5. So we have these two in series, right? And then whatever that value is going to be in parallel with this inductor, which whatever that value is going to be in series with that resistor. So I'm just going to draw this out. So that's what we have. And then I just did this part sort of to the side, so I'm just going to I'll swap colors here. I'll just have my markers ready to go right here so I can swap. There we go. So we'll take this guy. We'll do it separately so we don't get confused. So I did J5 times 10 minus J5 over 10. We add the values down here, J5 minus J5, so the J5 goes away. This is going to equal 25 minus J50 over 10. So we can, divide by 10, get 2.5 minus 5 minus J5. But our answer for this guy is going to be, so let's continue in black. So we're going to have 2.5 minus J5. This is this guy, right? And then we're going to add another 2.5. So our final answer for Z equivalent is going to equal 5 plus J5 5, and that's ohms. So that's part A. We'll box it. Sorry, that doesn't really look like an ohm, but okay, so part B, we'll continue over here. So part B is determine the RMS value of the phasor current IS, which is this current right here. So I just did Vs over Is is equal to the Z equivalent, and then we already know Vs, so we can solve for Is right away. So I'll just write it all out. Vs over Is is equal to Z equivalent. So that's equal to 5 plus J5, right? And then we're going to plug in for Vs. We'll basically get that Is is equal to 100 angle 0 degrees over 5 plus J5. And then that gets us the final answer of 14.14 angle negative 45 degrees, and that's amps. And that is already root mean square because we were working with the Vs, which we were given was root mean square. So we don't have to convert it or anything. Make sure you keep track of that on the final exam, because if you already have root mean square and you divide by square root 2, it's going to be wrong, obviously. So, okay, so we'll box that. Is everybody comfortable with doing this division? Why is the angle negative? So when we do this, we're going to get square root 50 as the magnitude, right? And then the angle is going to be positive 45 degrees. Because if we imagine our axis, the imaginary value is positive, so it's going to be up and over 5 and 5. It's going to get us 45 degrees. But then division, we know that we subtract the angles. So it's going to be 0 minus 45. So it's going to get us negative 45 degrees. 14.14. In his solutions, it's the same thing as 20 over square root 2. He just kept the square roots. Yep.
That's supposed to be positive for J5. Negative J times J is positive.
This value, so this you're saying this is supposed to be positive J5? Yes, that is correct. Sorry. Good catch. Yeah. Okay, cool. Part C is determine the load power factor. So the power factor, who knows that formula?
Power factor. The magnitude of S equals, wait, no.
Just the power factor.
Cos of
Yep. So we have the power factor, I'm just going to call it PF, is equal to cosine theta V minus theta I. So just remember that for the final. This is going to equal cosine. What is our theta V? 0. And then our theta I?
negative 45.
So negative 45. That's just going to be plus, right? So we're going to have cosine of 45 degrees, which is root 2 over 2. Or if you want to put decimals, I'm sure he'd be fine with that. I usually prefer just working with decimals, but it's whatever you guys prefer. Okay, so that's our power factor. Part D is determine the apparent, average, and reactive power absorbed by the load. So this is where we sort of need to know those formulas, right? So one thing I would recommend doing if you haven't already is work through all your previous notes, make like a good formula sheet for the final exam so that you're not flipping through all your notes trying to find stuff. Just get it all on 1 or 2 sheets of paper and then just use that basically for the final. Okay, so let's do this. Apparent power. Also, sorry, I'm a little under the weather, so if my voice sounds funky, sorry. So apparent power, does anybody know that? Just what that is equal to? V effective times I effective. So what is our V effective value? 100. Okay. And then our I effective?
14.14.
Okay. So that equals 1,414, which he just does 1,000 square root 2, same thing. And that, what are those units?
VA.
Yep, VA. So make sure you don't put watts. He may take off points for that. You're only going to use watts if you're doing average power or with the DC circuits. Or Pmax, right. Okay, so now we're going to do average power. So, anybody know the formula for that? Yep, so we're going to have V effective, I effective. It's basically just apparent power times our power factor that we used earlier. So we're going to have 1414 times 0.7071. That's equal to 1,000, and that's going to be watts. Okay, and then last, reactive power. I'm just writing these out just so you can use the symbols if you want. I just wanted to make sure you guys knew what each one was. Okay, so reactive power, formula for that, anybody? Yes, exactly. So we're going to have our apparent value up here, so 1414, and it's multiplied by sine of theta v minus theta I, which we know that theta v minus theta I is equal to 45 degrees, right? So we're going to have 1414 times sine of 45 degrees. That is going to get us 1,000 units. Anybody? What's that? Yeah, VAR. Which is pretty easy to remember, right? Because it asked for reactive power, so just add the R. Okay, so that is number 8. If you want to get pictures, get pictures. No, they didn't ask for the complex power. Right, so if they asked for S, you could just sort of put those together, right, and then make it into one. Complex, I think, is, well, you have 2 parts, so it's going to be one real part, so that's going to be watts if it's average, and then the complex part is going to be VAR. So, okay, so let's move on to number 7. Anybody want to get pictures? Go for it. I'm about to erase. How you doing? Ooh, this eraser is not very good. Okay. Number 7. Okay, that's everything. I can add. He added this just to sort of separate the load from everything else. Okay, so we know that Vs is equal to 100 angle 0 degrees, and that is not root mean square. We can assume that because it doesn't say RMS. So, okay, so part A is determine the load impedance value, Z low, so that the maximum average power is delivered to the load. So this is a problem where you can sort of do it a couple different ways. But basically what you want to do is whenever you get a problem where it asks for solve for the value of Z low so that maximum power goes through it, we want to find Z equivalent from the load's perspective and use that to solve for its value. So when we solve for Z equivalent from this perspective, we would open this source, or this source would turn off, which would lead to a short circuit, and then all these elements are in parallel. And then you can add a test source here and do it that way. Or what I did is I solved for V Thevenin first and then used that as the test source voltage to solve for Z Thevenin. I think doing it both ways would be helpful to you guys. We'll see. We should have enough time, so I'll just do it solving for V Thevenin first. So let's do part A. I did KCL. So everybody knows what it would sort of look like when we're solving for V Thevenin.
Are you given R?
Given R.
On the Vx, so we just get 20.
Oh, yeah, thank you. Yep, okay. So KCL, we're going to do VTH minus 100 over 20. So I'm just doing KCL at this whole node right here. Since I'm solving for V Thevenin, we still have to factor in this source voltage. If we were solving for Z Thevenin, which I'm wanting to do, so I'll do that after this. Although I don't have the notes, I just did it the one way, but we can do it. If I was just doing Z Thevenin, I would turn this off and then put that test source there. Let's continue. Plus VTH over negative J10, and that's equal to 0.05 Vx, and we know that Vx, I'll just put a little dot, is equal to 100 minus VTH. So we can plug that in. We'll get VTH over 20 minus 5 minus VTH over J10 is equal to 5 minus 0.05 VTH. Simplify that one more time. VTH times 0.1 plus J 0.1 is equal to 10. So then our answer is VTH. That gets us is equal to 70.71 angle negative 45 degrees, and that's volts. So we'll need this for later, so I'm just going to circle it. Okay. And so then now we're going to use that value to solve for ZTH. So, okay. I redrew the circuit. It's really not necessary, though. Since we're doing ZTH now, we're going to turn this source off. It's going to short. So we're going to have all these elements in parallel, and we're going to put a test voltage source here where the voltage is equal to V Thevenin. So I'm not going to redraw it. Where the load is. Okay, so I did another KCL with that. And it's actually, so the other way I was describing is we could just skip this step and do this with leaving V Thevenin as an unknown, and then we would just do V Thevenin over IS to solve for Z Thevenin, not knowing V Thevenin or IS, but we can still get an answer. So I'll do all this out, and then I'll show you if V Thevenin wasn't known. I mean, it's pretty easy. I'll actually write it out first. So it's IS. We're saying that this is IS, right? It's coming from our test source, so I'll just label that. Plus 0.05 VTH minus VTH over 10 angle negative 90 degrees minus VTH over 20 angle 0 degrees is equal to 0. So we could have just gone straight to this. And now it's just a matter of manipulating this to get VTH over IS. But we know VTH, so we're just going to plug in. So IS minus 3.5355 angle negative 45 degrees. I'm just sort of skipping ahead because I know you guys know how to do this stuff. Minus 3.5355 angle negative 45 degrees is equal to 0. So then we get that IS is equal to 10 angle 0 degrees. Okay, so we'll circle that because we also need it. And then we're just going to solve for Z Thevenin by doing V Thevenin over IS. So Z Thevenin ends up equaling 7.071 angle negative 45 degrees, or I'm just going to do 5. I'm just going to put it as 5 minus J5. And then whenever you're doing this power stuff, Z load is supposed to equal Z Thevenin, but you change the sign on the complex part. So Z load equals 5 plus J5. Remember to do that on the final. Yeah, remember we did that in one session? Yeah. Right. Yeah, we did that in one of my sessions. It changes sign. Does anybody remember specifically why? It's because of the law of cosines and sines. So cosine of negative theta is equal to cosine of theta, and then sine of negative theta is equal to negative sine theta. So it's specifically the sine property that changes the sign. So if you guys, I mean, you probably won't need to know that as long as you just remember to do that. Okay, so that's the value of Z load. So everybody understands how we could just have skipped this step, left V Thevenin as an unknown, and then solved for the V Thevenin over IS. Everybody understands that? We would get the same answer here. We would get straight to Z Thevenin, which we could change to Z load. Okay, so part B is determine the maximum average power that can be delivered to the load, and they actually give you the formula, which is nice. It's equal to okay, so this is really just a matter of plugging in, but there's one important thing to remember. So if we just used this value for V Thevenin, it would get us the wrong answer. Does anybody know why? Right, exactly. So we have to convert that to RMS because it's average power. So the key words there are average. Whenever it says average, you want to be using root mean square. So we're going to plug in 70.0 0.71 over square root 2, square that, and then divide by R Thevenin, which is 4 times 5. Sorry, this is supposed to be 4. I forgot that. And that ends up equaling 125 watts. Okay. Anybody have any questions on any of that? Where's the 5 from? So we're just taking the real part of the load. Whenever it asks for average power, you're just really taking the real part. Okay. Any more questions? Yep.
For the last part of the KCL, how do you have
Plus J 0.1. Where is that? Sorry. Here? Plus J 0.1. V over 20 minus.
the J10 up top? Right?
Let me double check. Plus J 0.1. Yeah, so I brought the VTH over to the other side. Yeah, so I just brought the J up top, and that made it positive. So bring this J up top. That changes the sign. Does that make sense? Okay. Any more questions? Okay. Do number 6 now. Okay, so number 6. Okay, this is a lot to draw. Oops. Worked a little lower than I originally planned. Oops. Okay, got everything? Yeah. Okay, so for this problem, I'm going to have to do it all over here. They want us to, part A, calculate the equivalent impedance, Z equivalent. So this is just a matter of doing all the parallel and series stuff. Use whatever formulas you want to calculate the Z equivalent. So for a problem like this, I wouldn't recommend trying to do everything together in one go. Like I did, I simplified this part first, and then I added them all together, solved for that, and then I did that part, together, and then I, took this apart, did this, solved for it, and then used those values to solve for all of it. So I'm probably going to be skipping ahead here a little bit. I'll just put in blue what I got to simplify these values. So this ends up equaling 4/5 minus j 2/5. And then this ends up equaling negative j4. And then that sort of simplifies it a little bit. Then you just have this whole parallel part to do, and then you just add that to that. So A is equal to 4 minus j2 parallel with 2 plus j4. Let me try to remember where I took off from. So I did. So this is these elements in series, and then that is this. So I just broke it down to that simple part. So then you end up getting 16 plus j12 over 6 plus j2. That ends up equaling 3.16 angle 18.435 degrees, which is equal to 3 plus j. So now we know, now we just have it simplified to 3 plus j here plus that element. So then that ends up equaling 4/5 minus j 2/5 plus 3 plus j, and that gets you 3.8 plus j 0.6 ohms. So that's part A. Box it. Part B. They want us to calculate the phasor current Ix if a 2 angle 0 degrees independent current source is connected to the terminals A and B. So we're just going to draw that. Okay. So we'll draw it up like that. 2 angle 0 degrees amps. So we're going to be using that to solve for Ix. So this is just solving for both Ix and Iy is just current divider. Iy, we're going to have to do it twice. So Ix is equal to 2 angle 0 degrees times 3 plus j. We can use these. This is where sort of separating everything comes in handy, because we don't need Z equivalent of the entire circuit. We just need the equivalent impedance for our current divider, which is just going to be this element combined, which we did up there, 3 plus j. So then because we sort of simplified it into different things, we can just look up, there's our value, plug it in, and use that rather than having to figure out from one formula where it is that 3 plus j, where that is in the formula, if that makes any sense. So this ends up getting you 1.414 angle negative 45 degrees for Ix. Again, I just work with decimals, but it's the same thing. And then Iy is current divider twice. And make sure on the final you really pay attention to where Iy is, because at first when I was doing all these, for some reason my mind put Iy here instead. So then I kept getting it wrong and I didn't know why. But then I re-looked at it and it's actually right there. So Iy, I called this, just to help myself out, I called this current I0 and solved for that. You don't really have to give it a name, but it sort of helped me. So I solved for I0 first, just using current divider as well. So 2 angle 0 degrees times 3 plus j over 4 minus j2. That gets you an answer of 1.414 angle positive 45 degrees. Then we're going to use that value for Iy. So Iy is equal to 1.414 angle 45 degrees times negative J4 over negative J2. That gets you the final answer of 2.828 angle 45 degrees amps. It's equal to IY. Okay. Does that make sense to everybody? Any questions? Yep.
For the first parallel function, when you do it by hand, are you doing the conjugate, multiplying the conjugate, or are you transferring it to?
Okay, so I transform it into the angle format. That's just what I prefer.
What about when it's like a negative degree at the bottom? When do you add it to 180? Like I'm confused whether you leave the.
Okay, yeah, I know what you're talking about. That's actually going to be a good example of that is one problem. Which problem is it? We're going to do it, and I'll show you. But it's really just like if you're talking about what I'm thinking, you'll get an angle, and then it's the same thing as if you added 360 to that angle. You know, it's the same answer. It's just trigonometric stuff. You know, you just add 360, and that gets you sort of the positive angle if you get a negative angle, if that makes sense. I don't know. I'm not sure on that. I've never heard that before.
Yes, I've seen a lot of examples that represent it, but of course some things have changed.
Right. So like one answer on this practice final, he had a positive angle. So at first I thought I got it wrong, but then if you just add 360, it's the same thing. We'll get to that problem. We'll eventually get to it. I forget which one it was, but okay. So let's get back to any question. You had a question, right?
Yeah, so when you define the impedance, you did it by hand or did you put it in your calculator?
I did it by hand. I'll just draw out what I did. So this is what you get when you do, I used this formula, 4 minus J2 times 2 plus J4. Sorry, it's really bad. And then you just add them together, so you'll get 2 plus J2. Up here you get, well, you should get 16 plus J12. Actually, not yet. So I just FOIL it, so you can save, so 8. That's going to equal 8 as well, so 16 minus J4 plus J16, so plus J12. What did I do wrong here? Oh, these are just added, so it's 6, not 2. So you get 16 over 6 plus J2. And then I'll convert that to, I prefer to convert that to angle format. So you do, just in case everybody or somebody doesn't know how to do that. So we're going to get the magnitude of it. So just 16 squared plus 12 squared, square root all that. You get 20. And then for the angle, you use inverse tangent. So opposite over adjacent. The opposite is going to be the imaginary component. The adjacent is going to be 16. So you'll get an angle of 36.87 degrees. And then down here you do the same thing. You get 6.32 angle 18.435 degrees. And then I just used that to get this. So you divide the magnitudes together, just as if they were normal numbers. But then the angles, you have to subtract this one from that one. Good. I just prefer doing that. What you could do also is just multiply by the conjugate of the denominator. So just multiply this whole thing by 6 minus J2 over 6 minus J2. And that should take you straight to 3 plus J. So it's just whatever you guys prefer. Okay. Any more questions? Nope. Okay. Erase, move on. number 5. Okay, get everything? Oh. Okay. So we're given that I1 of t is equal to square root 40 cosine 100t, and that I2 of t is equal to 2 sine 100t. So whenever I see, or sorry, is that, no, that's, I accidentally wrote down the wrong thing. That's just cosine 100t. Okay, so whenever I see sine, I just like to convert it to cosine right away. So that's equal to 2 cosine 100t minus 90 degrees. So now we're working with cosines, so we're good. Okay, so the problem just wants us to solve for Vx of t and Vy of t using whatever method you want. You can use mesh, you can use nodal. Usually when they give you the ground location, usually you want to go with, you at least want to try nodal first and see if it's easier. In a previous session, we've done it both ways. Some people prefer doing it mesh. I prefer doing it nodal because it actually works out to be fairly friendly. So I'll show you guys that method. I don't have the mesh written down. Nicole, you may have it, but we'll just stick with node first.
Wait, what?
The mesh, remember we did it this mesh way? You don't have your glasses. But we'll just stick with
With node, this way easier with node.
node.
Because you have to find Vx and Vy, and you cannot find it if you are doing it with mesh.
Yeah, so mesh, it's going to get you a current, and then you have to use that current to solve for Vx of t and Vy of t. So we'll just do node. Okay, so I'll do it all over here. So I do node at Vx of t. You'll get 1 is equal to Vx of t over 4 plus j2 minus Vx of t minus Vy of t over j10. Right. Yep. Oh yeah, let's convert those first. I almost forgot. So I'll just use blue. I'll just write it out in case any of you guys forget the formula. So what's the formula for capacitor converting to polar? Okay, so 1 over j omega c is equal to 1 over j times, what is our omega? 100. So we get that from our original formula. And then our c is 1 millifarad. So 1 millifarad, that ends up getting you negative j10 ohms. So this capacitor, you do the same thing. You get negative j4, 20 millihenry. You end up getting. So what's the formula for the inductor? j omega L, so that gets you J2. And then I usually just like to write, so that's equal to 1 angle 0 degrees, and then this is equal to 2 angle negative 90 degrees. It's equal to negative J2. Okay, let's continue now. So then what I do is I get a common, or I multiply both sides by 4 plus J2 times J10. So you end up getting 4 plus J2 times J10 is equal to J10 times Vx of t minus 4 plus J2 times Vx of t minus Vy of t. Then I do nodal at Vy of t. Negative J2 is equal to Vy of t over 2 minus J4 minus Vy of t minus Vx of t over J10. I do the same thing with this guy. So you get negative J2 times 2 minus J4 times J10 is equal to J10 times Vy of t minus 2 minus J4 times Vy of t minus Vx of t. Okay, so then I'm calling this 1 and 2, negative J10. Oh, I just changed, yeah, I brought the sign up immediately. Yeah. Good question, though. Okay. So I called that 1 and 2, and then I'm just going to show the simplified forms of those. So 1